So, good morning again, everybody. Today we are going to discuss radio waves and antennas. And as of such, we don't have such tasks in our course project. So, as I have already mentioned, we will not have any practical exercises today. Just some lecture material about radio waves, about types of systems, about antennas and types of the antennas, yes, about effects we can have with radio waves, which can have significant effect on the quality of the receiver and so forth. So let us begin with communication channels and more specifically with their classification. So as I have previously in the first lecture when we have met the first time told you, there can be very different classification types. So we can classify based on, for example, purpose of the system. So some systems are needed to transmit television signals, some are required to use phone communications. Telegraph is similar, but it transmits texts. Internet is completely different from these three, yes, and so on and so forth. So the idea is quite simple, yes, so based on purpose. Now, there also can be communication systems with different media where the signal is being transmitted. So we can have wired channels with cable or optical fiber. We can have wireless channels. Basically, this is, well, we can say a fancy word from radio systems, yes, and also laser systems. And we can also have acoustic channels where we are using acoustic sound waves. This is basically used in cases where we are not really able to use radio waves. And this is the example when the media is water. For example, in submarine communications, we have to improvise and use other approaches. We will talk about radio waves today. So basically, this excludes acoustic channels. However, we will mention also what kind of radio waves still can be used for submarine communications. It actually depends on the radio wave frequency. So obviously, for the type of the signal, we can have continuous signals, which are basically analog signals, and therefore we will have analog or continuous system. We can have discrete system, and basically these discrete systems transmit signal as samples. So we have already discussed that. And we can have discrete continuous systems. A nice example of such discrete continuous systems will be NRZ, Manchester, and all the codes we have discussed last time, which was 2 weeks ago. Yes, so there you also have data in a discrete or even digital format. However, for transmitting signal in channel, we are still using continuous or analog signals. Yes, these rectangular pulses signals are actually analog signals. However, they contain data samples. For example, here we have 1, here we'll have 0, which are artificially prolonged. This is actually very, very similar effect as to what we have been doing in our practical exercises by using Kronecker multiplication. Cron multiplication. So we had some signal, and then we decided to add a vector of ones, for example, 101 values. So this basically means that this magenta colored sample is just repeated 100 times, making an illusion of analog or uninterrupted line continuous signal. Yes, this is how we have modeled it in our mathematical software. But in reality, of course, this is a constant voltage level, which is not changing until the next sample is arrived. So there is a difference between continuous discrete and discrete continuous, which is something like in the middle between these two. Channels. Yes, we are talking about channels also. So, and finally, based on the signal frequency, we can classify these channels based on what frequencies are we using for making communications. And this is actually what we'll discuss right now in more details and see what are the differences, how this affects different systems, and basically also what types of systems can we use in different radio wave bands. So more specifically, first of all, I'd like to mention that based on the frequency as it increases, so our frequency is increasing in this direction. So here we have lowest frequency, here we have highest frequency. We are actually changing the type of radio wave. So these are classical radio waves, which are used as electromagnetic emitted signal, yes. Next, as we increase the frequency, we are slightly starting to move into the visible light, which we can actually see. But before visible light, we have the infrared emission, yes, which we are unable to see with our eyes. However, this is like a lower band of the optical waves, yes. As we increase frequency even further, now we start working with optical signals, which are basically lasers and optical fiber, yes. And if we would like to increase it even further, then we eventually would end up with some X-ray, which we don't still have technology to use as signal for transmitting information for now, but in the future maybe we'll increase this frequency even further. So yes, here I'd like to mention our motivation. Why do we try to increase this frequency all the time? So why exactly optical signals are so good for us? Well, of course, the mechanism of the propagation is slightly different for optical signals than for radio waves, because we have the optical cable and the usual noise doesn't really apply to this signal. But there is actually a little bit more to this than just the noise immunity. So the thing is that each transmitted signal requires some frequency band. For example, here. And you actually have confirmed that yourself in our previous practical exercise part when we have calculated the spectrum of the transmitted signal for your course project. There you had, each of you had different parameter of tau, which is one symbol duration, tau, and this symbol duration actually significantly affects this bandwidth. So basically it's reverse of these pulse, yes. So the shorter pulses we are starting to use, the wider and wider bandwidth we must provide. And naturally, there is only a limited resource in the frequency. So for example, for a specific system, we can start using our frequencies starting from here and ending from here, yes? So it's not difficult to calculate how many actual users will be able to use the system simultaneously at the same time, yes? And the number of such users will always be limited. Now, the thing is that nowadays we also want to transmit faster and faster. So our data transmission rate, which is also expressed as the reverse of symbol duration, yes, is now measured in gigabits, for example, or even tens of gigabits, or for some magistral networks or backbone optical networks, it can be even hundreds of gigabits or even terabit per second. So this requires us to make these pulses shorter and shorter. As of such, proportionally, the bandwidth will also increase. So we need to have this band where we can work. And the thing is, the lower frequency we are using, the more narrow this band is. So in order to have a wide band, we have to increase our frequency. So that, well, the simple example, consider that we are working in 1 megahertz frequency range. So there is absolutely no way how we can put 1 gigahertz bandwidth here. So if we try to put 1 gigahertz bandwidth here, it will go here in negative frequencies, yes, which do not exist. So we cannot really put our spectrum into these narrow bands. We have to have here at the very least 1 gigahertz frequency. So this automatically gives us some restrictions. And now this is just one user. If we'd like to have 10 users, then we'd better work with 10 gigahertz frequency. And again, this will occupy all the radio band. And basically no other system will be able to work here. And as you know, we have many systems. We have GPS, we have Wi-Fi, we have cellular communications like LTE and so on and so forth, and they actually share the frequencies. So basically, yes, if we want to transmit data faster, then we actually have to use higher frequencies. This is also technologically not a simple task. However, in recent 2 last decades, we have actually made some progress there, and we are able to use, for example, 80 gigahertz radio waves with so-called E-band frequency range for microlink antennas. We'll talk a little bit more about that. However, they work very similar to laser, because as you can see, as the frequency increases, super high frequency range here is limited by 30 gigahertz. We actually, with 80 gigahertz, are very near to infrared and optical signals, which require direct visibility for the system to work. So basically, we can tell that our antennas are working like lasers. And this is a good replacement where you cannot really make optical cable. For example, in some mountain regions where it is very difficult to make optical cable. Yes, so we are using then relay transmission, meaning that we have some stations, yes, some antennas, which just passes through information and so forth and so forth. So hopefully this has provided you some clarification. Why do we want to increase this frequency? Because there are just too many users to put them all into a narrow band. That is one thing. And another thing is that we want to transmit data faster and faster. So this also requires more frequency bandwidth. So let us talk more about specific radio frequency bands which we are using today. So first of all, I'd like to remind you that radio waves are electromagnetical in their nature. So this means that we have two fields existing at the same time. We have electrical field and we have magnetic field, and they, how to say it, not improve, but induce each other, yes, and this way our electrical field produces magnetical field produces electrical field, and so forth, and therefore this wave is propagating from transmitter to receiver. So this is, of course, you had a lot more in electromagnetism or physics course, so hopefully you can remember that. However, will be most interested here right now in the frequency of these radio waves. So these radio waves have both the frequency, which is measured in hertz. This is the number of oscillations per second. So here we have 1 oscillation per 1 second. So that would be 1 hertz. If we have 10 oscillations per second, 10 periods, then that will be accordingly 10 hertz and so forth. And also we have the wavelength. That is the distance the wave travels during its single oscillation. So basically this is lambda meters. So considering we have the propagation speed of the electromagnetical wave, it is possible to know what distance will be covered by electromagnetical wave with a specific frequency. So frequency, as you know, is reverse of the time, 1 divided by period. So here basically is nothing other than our school form, where we can calculate the distance based on traveling speed and the time it takes to travel the distance, yes. So this time is actually converted into the frequency, and therefore we have this expression which relates to each other the wavelength and the carrier frequency. So carrier frequency means that this is actually the center of the frequency band, very similar as in your course project example which we have calculated last time. We had some carrier frequency specified for you, and around this carrier frequency you have calculated your spectrum, for example, for binary amplitude shift keying, yes? Now, we didn't yet discuss where exactly in our spectrum we are putting a limit. So here I have arbitrary limits. However, we'll talk about that. But I think it's quite obvious to you that we need to have our limit optimally in a way that the most part of the signal energy is located in this main side lobe of the spectrum. So this is actually where we are going to put the limits for our spectrum. This part, however, although improves the shape of the signal, so we'll have more like a rectangular shape signal like this, instead of, let us say, just a harmonic signal. But for telecommunication signals, this is not really that important. We'll prove that later, that actually it's sufficient to have just a first harmonic of the signal to actually being able to tell where is the 1 symbol and where is the 0 symbol. Here is 1, here is 0, here is also 0. It's sufficient, and it also, well, is preserving this frequency band, making it as small as possible. So you can see more about radio spectrum classification on this webpage in Wikipedia, yes, and there are actually, based on the frequency bands, multiple classifications. Today we are going to discuss ITU classifications, but there are others as well, and you can watch them into this link. So, for example, I was mentioning some E-band frequency, yes, and I told that we have 80 gigahertz here. And indeed, as you can see, the E-band is actually from 60 to 90 gigahertz, and this is for NATO, yes, classification. Or no, NATO classification is here. Here is another classification in practice, yes. And here we can see gigahertz. Not really here. Okay, it's really difficult to tell what exactly that classification is. It's some practical bands which are used by manufacturers of radio equipment, because I was actually also working some time in radio equipment production in Latvia, and they also were working on E-band. Also, you can note that actually E-band also is here as well. So it has two ranges. Yes. Okay, but we are going to discuss the classical ITU classification based on the frequency. So the idea here is very simple. Let me again open up the entire table. So we are working on decades of the frequency. So we start with frequencies from 3 to 30. Next frequency range is 10 times greater. Next one is, again, we multiply all the numbers by 10, and so on and so forth with each step, yes? And also, at the same time, we can see that as frequency increases, the wavelength decreases. So let's start with the lowest frequency band from 3 Hz to 30 Hz, and accordingly wavelength is measured in hundreds of kilometers. Well, tens, thousands and hundreds of thousands of kilometers. That is very long distance, yes? So basically one period is taking forever to transmit, yes? And basically it travels, well, not actually forever, it's just a speech figure, yes? But it travels a lot of distance before it ends, yes? So here I'd like to mention one important thing about this wavelength, that when we'll discuss antennas today, you will mention that actually most of the antennas in their physical dimensions are one way or another related to this wavelength. So it's very common practice to make antennas with length of lambda divided by 2. So, as you imagine, if we have here tens of thousands of kilometers, it is very difficult to make such antenna which is taking this long distance. However, not really impossible. We can actually use our power lane cable lines as antennas. So basically this cable which we are using to get electricity to our houses, yes, can be indeed in thousands of kilometers for large countries such as United States of America and so on and so forth. And also the frequency is not really 60 or 50 hertz, which is our power frequency, yes. So it can be separated and transmitted in the same cable. So yes, it's still possible to make such antennas, but it will of course require very, very long cables. So yes, and the specifics of this radio frequency or band is that it can actually travel through water. So it is possible to make communications with objects that are underwater, submarine communications. So this is still possible. However, the frequency band here is just 27 Hertz. 27 Hertz. So just for you to understand it better, let us take a usual speech signal. So I'm talking to you right now using my microphone. The signal is converted into digital form, but we can also assume that we are not transmitting signal in a digital form. We can make an analog signal. So in that case, the specifics of human organs are such that we produce acoustic waves of the frequency starting with 300 Hz and ending with 3400 Hz. So this is a normal speech. We are not talking about some opera singing or other higher tonality signals. Yes, we are just about normal talking in normal environment. Yes, so this more or less for each of the human individuum is the same. And this alone requires 3100 Hertz, which is completely impossible to put into these limits. Yes, so no verbal communication is available with underwater objects in this frequency range. So basically what we send is some beacon signal, yes, just to know for this submarine where it's swimming and whether it's approaching or getting away. Yes, so we can imagine that here we have some submarine. Yes, here we have some beacon which transmits this signal to submarine in the form of just a harmonic signal, for example, yes, and this harmonic signal is used by this submarine to actually position itself better. Yes, so no really important other information can be transmitted in this narrow band. Now, situation here is now a little bit different because previously our first band was like here, up to 30 Hertz. Next band is, well, basically up to 300 Hertz. So you can see that actually the frequency band for our information signal is now much wider, and we can actually send some data very slowly, but still we can now provide some data. Still, we cannot really send speech signal in this narrow band, or rather analog speech signal, we can try and use some compression methods, which may be able to be used for this purpose. But you need to actually consider that as the frequency increases and wavelength decreases, the ability of these electromagnetic waves to pass through water also is becoming worse. So this range is not so good for underwater communications as this, yes, because basically we are having too much loss in our signal during the transmission. So yes, so the distance where it can travel is also more more limited, let us say. So yes, it's less. So as we increase our frequency, so decreases the decreases the wavelength and increases the frequency. We are still somewhat able to use this communications for submarine communications. Now, probably with using some compression methods, we can actually transmit voice signal here. Yes, because basically voice, as I have told, is around 3.4 kilohertz, the upper limit. So most of the spectrum of the human voice can be actually put into these frequency bands. Yes, it will be not natural voice. You will maybe have some difficulties recognizing who is talking to you, but for some military operations in underwater, it may be not really important. Yes, it's important to actually transmit some meaning, yes, some information rather than who is talking to you. So yes, now we can use voice communications here also, but as I have told, the performance of these electromagnetic waves underwater even more degraded, so distances are also not so great. Yes. Also, we can use these communications in mines under Earth. Yes, because well, there we have a lot of obstacles, and these waves are trying to travel around these obstacles. Of course, distances will be very short because we'll have to use small antennas. We are going to not use these lambda divided by 2 antennas because this is just too ridiculously large large antenna to carry on with person, for example, in mine. So as of such, if we don't use this wavelength, yes, we will not have energetically effective antenna. So it will require much more power than this antenna to transmit signal, and this signal will also be much it will degrade much faster, it will be weaker, and so on and so forth. So basically, we are not really obligated to use this as the length of our antenna. However, if we don't, then this antenna will perform worse than this half wavelength dipole antenna. We'll talk about antennas at the end of today's lecture, so hopefully it will become more clear to you. But for now, it's just an observation. You need to consider that the energetically effective antenna actually is related to this wavelength. So it's quite simple then to calculate that if, for example, we use our small devices nowadays, so let us say we have 5 centimeters antenna acceptable for us. Well, maybe you have seen some old phones with external antenna, which is a little bit out of the phone. Yes, some part of the antenna is inside, some part of the antenna is outside. So we can calculate what wavelength and what frequency band that will be. And eventually we'll get to there with this classification. So let's go further. So currently, as you can see, very specific, very specialized systems, and well, nothing of what we are using in our daily life yet. So let's go further. We are still to some extent able to use submarine communications, but more likely in this 3 kilohertz range than into this 30 kilohertz range, because 30 kilohertz is already almost not really usable for underwater communications. So we are, for underwater communications, might take some part of the spectrum, but not all of it, yes. we are here now more working with geophysics, yes, geological processes of some sort, some navigation systems which transmit very slow signals as beacons for aircrafts, for other users. They are not GPS systems, so it's not global. It's some local systems. So, for example, you have some airfield, yes, you have some beacons in this airfield, and this produces some navigation signal for your aircrafts to maybe better understand this landing line, yes, and so on and so forth. So this is local navigation systems, so not GPS, yes. This also includes precise time signals, yes, which is more precise than usual time used, which you can see in our clocks and so on and so forth. Again, these are some specialized systems, mainly related to some airports and other things like that, yes. Also, we can mention here that actually heart rate monitor is also working, wireless heart rate monitor working in this frequency range. So this is something more closer to our daily life. However, I believe not much of you are using these heart rate monitors in the daily life. So again, it's still very specialized equipment, yes. Now, we don't use anymore our communications underwater. We now are starting slowly to approach to actual radio transmissions, which we can receive and listen to, yes. So again, the frequency range is now hundreds of kilohertz. The antenna size is now, well, this is not really antenna size, this is wavelength, yes, which can be related to antenna size, is much more forgiving, yes, for our not kilometer long antennas, yes. So again, we are using this for navigation, for time signals. Now, RFID, yes, which is basically wireless payment cards, wireless identification cards. These are working on a very small distance. You actually need to put your card almost precisely to this receiver, yes, for it to be able to read. Mainly because, well, we are using such frequencies, yes, first of all, and secondly, because we actually need to use this card as the transmitter as well, and we don't have any power elements in our cards, so all the effects are based on the electromagnetical inductivity, induction effect, yes, so that we are receiving some radio wave from our reader, which induces some current into our chip, and this current is used to actually provide this information to chip as a very, very weak signal, because obviously the size of your card is not in kilometers yet. So this is actually something we are using in our daily life, yes, RFID identification, RFID payments, and so on and so forth. The idea here is based on the principle of electromagnetic inductivity, yes. Also, some amateur radios are working in this range, yes. So basically, you are able to send some voice, some music. The frequency band is more than adequate for this, yes. Some amplitude modulated radio was working in this range with specifically long wave range, yes. So we'll talk a little bit later about what waves can be considered long, what waves can be considered short. There is actually nice explanation video which we will watch together, which will explain where is that frequency or wavelength limit when the waves becomes long, where it is short, and so on and so forth. This is related to some physical processes. So basically, this is actually working. Nowadays, we don't really use AM radio. As you may know, we are currently using FM, frequency modulated radio, with much higher frequencies as well. But still, in some 50, 60 years, yes, this, when radio was only beginning to be used, this was actually used, and also it was quite nice. For example, for USSR, yes, which was quite a big country. It was possible, for example, to have this transmitter in Moscow, and it will reach all the places around this union. Yes, so this was possible to transmit this radio over very large distances, in maybe even thousands of kilometers, because of the specifics of these long waves, which can travel basically around all the world. Yes, so this was the idea of a radio station which can be received in any place, basically. Yes. Okay, so we increase even further our frequency because time passes on. We have more and more radio stations. We have more and more users, and we have need for higher and higher frequency bands because we need to transmit data faster and faster. So yes, we are basically forced to use higher frequencies. Also, at the same time, I'd like to mention that our equipment improves, our technology improves, so we are now able to make these generators working at higher frequencies. So actually, at some point, we are becoming capable of using these frequencies, because maybe previously, in some 50 years and 60 years, yes, we had no technical means to use such frequencies. But now, of course, we can use gigahertz and even tens of gigahertz, and we'll see about that when we get there. So what's here? Some avalanche beacons, again, amateur radio, amplitude modulated radio. So basically, this is just some radio. Yes, radio as of device which we are using to listen to some music, to some news, and so on and so forth. Well, we increase frequency even further. And again, we have here RFID as well. Now we have short wave radio and radars. Aviation communications, basically, yes, are used in this frequency range between dispatcher and crew of the air flight, and also on ground communications in airports, yes, are working in this frequency range, which is dedicated to these needs, and accordingly, other systems are not allowed to work in these ranges. So what you need to understand is that actually there is some licensing question as well. Not all systems are allowed to work in all frequency range. Some frequency range are dedicated to specific systems. For example, you cannot, well, not that it would really provide you good data transmission rate, but also if you could, for example, you cannot really make Wi-Fi transmitter for Wi-Fi computer networks in this frequency range. It's just not allowed. But also, as I have said, it wouldn't really do much good. Maybe it would. Well, actually, yes, Wi-Fi channel can be 20 megahertz, so this range actually contains enough of the bandwidth for one Wi-Fi channel, yes, and well, it will occupy all the frequency range, and well, it's not allowed. Yes, we have another frequency range for Wi-Fi. So as we go further, we can see more and more our daily and commonly used systems. Yes, so now we are talking about very high frequency range, and here we are having our daily radio which we can listen to. For example, in Latvia we have these radio stations around 100 megahertz. Probably in France it's also something like that, maybe 200. I honestly don't know, but now you can actually pay attention and check what the frequency is of your favorite radio station you are listening to. Of course, naturally, each radio station has a little bit different frequency, yes? Here also is television. We are talking about television which is received with antennas, yes, not satellite antennas, just regular antennas. Now, again, aviation communications, specifically ground-to-air communications, amateur radio also. Well, this amateur radio doesn't work over large distances, so although it's not really, how to say it, not really a system like much people use. Some people are using these radio waves to communicate with each other maybe, and so on and so forth. So this is very specific topic of amateur radio. Yes, some people make with their own hands some equipment. This is, well, basically some hobby, yes, I can say, mostly for people, and they can also use this band for communications. So now we have gotten to the frequency range, which is really densely used today. This is ultra high frequency range. And this ultra high frequency range has the specifics that actually it can pass the ionosphere of our planet, ionosphere, and go into the space. So basically, these communications can be made with satellites. And not all frequency bands previously were able to pass through ionosphere. Some communication bands are reflected from the ionosphere, and there is no way to send a signal into the space. Of course, this actually also depends on the angle of this radio wave, but more or less these frequencies can be used to actually pass the ionosphere. And this is why here we have satellite navigation as well, such as GPS, Galileo, GLONASS, and so on. We have satellite radio here as well. Yes, satellite television is in higher frequencies, so no satellite television here. Also on the ground we have cellular communications, so both the 2G, 3G, 4G, all of them were working in these frequency bands. Well, 4G actually extends beyond this band, but it also has some modes. Yes, it has different modes. It uses actually multiple frequency bands, depending on the country, depending on your location, depending on the equipment, and so on and so forth. Yes, so it can actually work both in this frequency band and in next one as well. So this is again television, some radars, radio relay stations. Radio relay stations use radio to transmit data over long distance. Yes, where optical cable cannot be made, for example. Some microwave devices which are used for this radio relay, and so on and so forth. So basically, yes, and Wi-Fi networks, Bluetooth is also working with these frequencies. Well, for Wi-Fi networks, we have two frequencies, 2.4 gigahertz and 5 gigahertz. As you can see, 5 gigahertz is outside of this frequency band, so it will go to the next one. But 2.4 gigahertz is actually in this band, yes, it's lower than 3 gigahertz. So we go further, and here we have again cellular communications, but these are newest standards like 4G and even 5G will also operate in this frequency band. Yes, also what I wanted to actually mention is that our antenna size now is, well, can be at least, yes, in centimeters. Yes, so for example, if we use 3 gigahertz frequency, then wavelength will be 10 centimeters, and that will actually produce us those lambda divided by 2, 5 centimeters, which is acceptable size for the antenna to be effective. Yes, as it goes further, it's easier and easier to make these antennas. Yes, so here you can see that actually from 10 centimeters to 1 centimeter, antennas are very small in this case. So we are using this for Wi-Fi as well, which is 5 gigahertz range, for road traffic communications. Yes, so you can imagine you have cars. Yes, in intelligent transportation systems, you have some infrastructure, maybe some, green light, red light, and so forth, which sends data in addition to actually showing with the color with the traffic control. Yes, it can also send signal to each of the cars. Maybe some car, for example, this car cannot really see this signal visually, but it can get the signal. Yes. In addition to that, cars can communicate between each other too. Of course, for this to work, the car has to be equipped with this equipment. But basically, this is something we are currently working on as well in our field, yes, in telematics. So yes, this is something world is working on to actually provide communications for car, and maybe in some future it will be mandatory for each car to have this module to be able to participate in these communications in RAW. So this is called dedicated short range communications. So it's not expected to work in kilometers. It's working really like Wi-Fi modules in hundreds of meters, and that's it, yes. So radio astronomy here is as well, because, well, in order to be able to receive this signal, it actually needs to pass through ionosphere. Yes, satellite communications and satellite television as well. Here, some radars, which are used to detect moving objects, and so forth. Now, as we increase frequency even higher, we are using less and less systems. So as you can see, there are no more things like television, like radio, no more cellular communications, just some specialized things like radio astronomy, some experimental wireless networks, so for example, AD standard, which can work at these frequencies. Now, these frequencies require direct visibility, so it's hard to use Wi-Fi networks at these frequencies because it needs to have clear visibility. You don't need to have any walls obstructing the path of the signal, so it's difficult. Also, given the fact that wavelength is now in millimeters, yes, in any object which has size of millimeters can actually provide how to say it, obstacle, yes, for our signal. So that's why for satellite communications we have this effect of meteorological effect. Yes, for example, if it's raining or snowing, then performance of satellite television is being degraded because of that, because all these obstacles are their size is well related to the wavelength, and therefore this can interfere with our signal, yes, physically making it to disperse, to what was called diffract, yes, and so on and so forth. Now here we have road radars working in this range. So this is what the road police is using to measure the speed of your transport vehicles, which is somewhat used to, yes. Microwave radio relay, again, 80 gigahertz is actually in this range of that microwave stations I was talking about, yes. And in this band, it's actually not a problem to send, for example, 10 gigahertz frequency band, which accordingly would give 10 gigabits per second. Yes. So again, it needs to have direct visibility, and the meteorology also affects the performance. But still, in some places where you know it's not raining, in some desert, for example, yes, and mountain regions maybe. Well, mountain regions can have rain, yes, but still there may be no other alternative, like making the optical cable in this mountain may be difficult. So for example, you have mountain and you need to send signal over this mountain. You wouldn't dig through all this mountain to make the optical cable. No, instead you are going to use the microlinks to transmit the signal this way, yes. Directing antennas so that they have direct contact, yes. And this way it will be much cheaper. Yes, of course, it will be not so good as optical cable, not in terms of the data speed transmission, but in terms of these meteorological effects. But still, sometimes it may be the only possible solution. So this is radio relay. We can increase frequency even further, but this is mostly experimental frequency range. Yes, it's now in terahertz, and we are really getting close to the infrared frequency. Yes, so this is for experiments like in medicine, physics, computing, and so on and so forth. Yes, I think there can be more. Yes, more information Wikipedia here. Yes, so in medicine, we are trying to use this to replace X-ray. As you know, X-ray is not really healthy for us. So there are some research made on how to make it not so harmful for us. Yes, and also, now I don't remember in which particular frequency range it was, but there was some. Okay, maybe I think we can now have our break, and after break I will be able to tell you a little bit more about it. So yes. Yes, now we can have some break. So let us have a break of 15 minutes and we'll then continue at 9:25. Yes, so see you in 15 minutes.